Good morning, everyone. Let's get started. So in the previous class, we were talking about distributed lossless compression of correlated sources. So we looked at the two user problem or two source problem where you have two different files, xn and yn, which are correlated with respect to each other. Their IID across the i's, that is the components of the vectors are all IID, but xi and yi are correlated with respect to each other. So we assume that xi and yi are jointly distributed according to some PMF pxy, which is known to both the first user and the second user. And the goal is to compress these files separately. So you have separate compressors for each of these two files, but you can do decompression jointly. So the compressed files are given to a single decompressor, which has to output the original files xn and yn. All right, and our goal is to understand under a vanishing probability of error constraint, what is the smallest R1, R2, the smallest rates that we can achieve for this compression problem. And in the last class, we saw that if we didn't really care about the fact that decompression is done jointly, if we decompress the files separately, then obviously R1, R2, R2, certainly this rate is achievable, h of x. So in fact, any R1 greater than or equal to h of x and R2 greater than or equal to h of y is achievable. So that corresponds to this, the rate region corresponding to this region over here, the green region. And we saw by way of some of the converse or to the source coding theorem, by combining the sources and making use of side information, that no rate pair in the red region can be achieved. Right? No matter what you do, it is impossible to achieve any rate pair in the red region, and that is because even if you have more powerful encoders which sort of encode things jointly, the red region is not achievable. Right? So the question was, what happens in between the green region and the red region? So in particular, this region over here. So in this class, we'll see that every rate pair in this region is actually achievable. So in fact, you can do better than decompressing them separately. You can do some kind of a joint decompression. You can do independent compression, but joint decompression, and in fact lower the rate. Right. So one point I'd like to emphasize over here is that although we're getting these rates which are lower than h of x, h of y, this is only under this probability of error constraint. So we can tolerate a vanishingly small probability of error. The probability of error is not exactly equal to 0. But on the other hand, in general, for general sources, if we want to do variable length zero error compression, then in fact it is not possible to do better than R1, R2 equal to h of x, h of y. So really it is this probability of error, this vanishing but non-zero probability of error, which allows us to obtain better rates. So the probability of error is greater than 0, but we demand that the probability of error tends to 0 as n tends to infinity, and actually this lets us obtain R1, some R1 less than h of x and some R2 strictly less than h of y. And generally speaking, this cannot be obtained So by this I mean that R1 less than or equal to h of x and R2 less than h of y. This cannot be obtained if we demand that the probability of error is strictly equal to 0 and allow variable length compression. Okay, and this is an important point to note. So unlike the point-to-point case where we saw that the best rates that can be achieved are equal to h of x is achievable if you have a single source and a single compressor and a single decompressor. Even if you do say fixed length compression with vanishing probability of error or variable length compression with zero error, asymptotically the same rate can be achieved. The best rate that can be achieved is equal to entropy. But for distributed compression of correlated sources, for fixed length compression with vanishing probability of error, these rates strictly less than h of x, h of y can be achieved. But generally speaking, if we want variable length compression and zero probability of error, then we cannot do any better than h of x, h of y. All right. Okay. So in this class, we're going to see the achievability proof of this result. We'll show that everything which is not in the red region can actually be achieved. There are compressors and decompressors which allow you to achieve any rate in this entire big blue region. Okay. So before we proceed with that, are there any questions? All right. So, first note that to show that some rate region is optimal, we need formal proofs of two statements. One, that no point in the red region is achievable, and I gave a semi-formal proof of that. I'll let you prove it formally on by yourself, and I'll post that on Piazza as well. But now let's see why every point in this blue region is actually achievable. We want to prove the achievability part of it, by which I mean that we want to show that there exist compressors and decompressors which allow you to achieve any rate in with satisfying these three constraints. Okay, so want to show that there exist encoders and a single decoder, or basically a sequence of encoder 1, encoder 2, and decoder, such that the probability of error, in fact, we show that the limit of this probability of error is equal to 0, and the liminf of kn by n is equal to, let's say, R1 plus epsilon and ln ln by n infinity is equal to R2 plus epsilon. So fix some epsilon greater than 0. So we want to show that this happens. It's actually possible to construct encoders and decoders where encoder 1 is a map from, let's say, xn to 0, 1 to the kn. So it takes n symbols and outputs a sequence of kn bits. When this kn is a function of n and the joint distribution, it's fixed beforehand, but not dependent on the realization of xn. Similarly, encoder 2 takes n symbols and outputs a binary sequence which corresponds to the compressed file, and the length of the compressed file is some ln. And we want to show that asymptotically kn is roughly nr1 and ln is roughly n times r2. Right? And at the same time, the probability of error can be driven down to 0. Okay, so once again, we'll use an approach similar to what we did for the channel coding theorem. We won't be able to show the existence of, we won't be able to say exactly what is the best code, but we'll show that there exist compressors which basically choose a random code and show that on average the probability of error is vanishing in n, which implies that there exists some code for which the probability of error is vanishing in n. Okay, so this is what we have to show, right? And the sort of approach we'll do is as follows. Now let us see what does the compressor have to do. Okay, so the compressor is basically a function from xn to 0, 1 to the kn, and encoder 2, the compressor 2, is a function from yn to 0, 1 to the ln. Okay, so basically what we have is that a compressor essentially is the following. So look at all possible sequences x. So let's assume that x is, say, 0, 1, 2, and let us assume that y is also 0, 1, 2. Okay, so corresponding to each sequence, so the all 0 sequence, 0, 0, 0, 1, 0, 0, 0, sorry, 1, 0, and so on, all the way up to the all 2's vector. So there are size of x to the n possible sequences. So these are all possible xn's. Right? So corresponding to each xn, we have to identify a particular code word. Right? So this has length n. These are all possible messages, or in other words, all possible input files. And these are all possible compressed files. So C1 kn. So maybe this is mapped to the all 0 sequence. This is mapped to 0, 1, whatever. So we have to basically identify the right mapping from this sequence to this sequence. So maybe this is 1, 1, 0, 1, 0, 1, and 0, 0, 1, 0, 1, 0, something like this, right? So we need to find out what is the code word or the compressed file corresponding to each of these sequences. So each of these has length kn. All right. Similarly, encoder 2 has to do something similar. So for each yn, encoder 2 outputs some compressed file or some code word of length ln. right? And this is mapped to something like this. Okay, so obviously, if since kn is less than n, there'll be multiple sequences over here on the left which get mapped to the same code word, right? That has to happen. But that's okay, as long as not too many sequences on the left get mapped to sequences on the right, it's fine. Right? And in fact, we'll see that there are actually many sequences on the left which get mapped to sequences on the right. But since we're decoding them jointly, things turn out to be still well and good. Okay. So basically, we just need to construct this table, right? These two tables for xn and yn, right? For encoder 1 and encoder 2. Correct. So basically, encoder to identify encoder 1, we need to identify a particular code word for each input sequence on the left. Encoder 2, for every so we need to identify these code words for every sequence on the left. Okay, so that is what encoder 1 has to do. Encoder 1 and encoder 2 have to do. And to design the decoder, we need a similar map. So given a pair of code words, so these code words are sent to the receiver. The receiver sees a pair of code words and has to identify which xn and yn were actually compressed, or which xn yn were actually transmitted. All right. So that is the so basically we need to identify what pair corresponds to a particular code word and what particular pair of code words correspond to a particular xn and yn. Right. So is this high level description clear? All right. So now I'm going to choose these. I'm first going to choose an R1, R2, which is in the blue region. Okay. So R1 is strictly, let's say, greater than or equal to h of x given y. R2 is greater than or equal to h of y given x, and R1 plus R2 is greater than or equal to h of x comma y. And then I'm going to choose a sequence of kn and ln. So choose R1 comma R2 in the blue region. And you choose kn such that the limit kn over n is, let's say, equal to R1 plus epsilon, and limit as n tends to infinity, ln over n is equal to R2 plus epsilon. Okay, so this is what we are going to choose. Now, suppose that I have done this. Now let's see how do you identify the encoder or the code book. Right. So for each, so we're going to use a random code book. Okay, and by that, what do I mean? So for each sequence xn, so remember, keep this in mind. So you have xn, which needs to be encoded. Yn is separately encoded, but these are jointly decoded. Right? So for each xn, you generate the corresponding code word C1 kn corresponding to xn uniformly and IID at random. IID uniform over 0, 1 to the kn. So basically, you draw a code word uniformly at random. Okay, so similarly, for each yn, you generate C2 ln. The corresponding code word is drawn at random. Okay, so basically what are we doing? So we have the set of all possible xn's, right? We have the set of all possible xn's, and corresponding to this, the encoder has to identify the code words. So this is xn, this is C1 kn. So these, so basically encoding corresponds to just identifying this table, just populating this table. And what we're saying is that this table is populated uniformly at random. Okay, so that is basically what we're doing. Okay, so similarly for yn, so you look at all possible yn sequences. So corresponding to each sequence, we need to identify a corresponding code word, which is C2 ln, and basically we're just drawing these code words at random. So for each, this is a uniformly random sequence of bits, this is a random sequence of bits, and so on. Okay, so this, by this we generate the code book. All right, so these are the code books which are randomly generated. Right? And once these are first randomly generated and they're shared to both the encoder and decoder. First, even before seeing the messages, even before doing any sort of encoding, you just draw one code book at random, share it between the encoders and the decoder, the senders and the receiver, and then you start compressing. Right? So these are shared among encoders and decoder. Okay, so both the encoder and decoder are given these code books, so they're given these tables, and they're going to use these tables to encode. The encoders are going to use these tables to encode. So this completely specifies the encoding process. Right? Once you draw a code book, this completely specifies the encoders, encoder 1 and encoder 2. Okay, so with this we need to now see, okay, so now that you're given these encoders, you need to define what the decoder is going to do. And the problem here is that there could be multiple sequences or multiple pairs of sequences which could correspond to the same pair of code words. So note that there are the total number of pairs of sequences. So what is the number of possible x and y in pairs? So what is the number of possible x and y in pairs?
So cardinality of x into cardinality of y.
Correct. So it's cardinality of x, cardinality of y, whole raised to the n, right?
Yes, sir.
So this is the number of possible x and y in pairs, right? But what is the number of possible code word pairs? So C1 Kn, C2 Ln. So these are binary sequences. Yes.
So to the power K1, Kn plus Ln.
Sorry.
2 to the power Kn plus Ln.
Correct. So it is 2 to the power Kn. So there are the number of C1 Kns is 2 to the Kn. The number of code word C2 Ln is 2 to the Ln. So the total number of pairs is 2 to the Kn plus Ln. And this is going to be much less than the size of x to the n, size of y to the n. Right? So there is so it's high probability there's going to be a collision. Right? So what is the average number of xn, yn for each code word pair? The average number of sequences which are going to average number of messages which are mapped to a particular code word pair.
Sir, it's basically a ratio of code word pairs by total possible x and comma y.
Exactly. So it is 2 to the kn plus ln divided by size of x the n, size of y to the n, and this is basically going to be roughly whatever 2 to the nr1, 2 to the nr2 divided by size of x to the n, size of y to the n. Right? Or this is essentially equal to 2 to the n times r1 plus r2 minus log size of x minus log size of y. right? And what we're aiming for is something where R1 and R2 are much smaller than log size of x and log size of y. Okay, and we'll see that even with this, it's actually possible to achieve vanishingly small probability of error. So let us now see what the decoder is to do. So the decoder does the following. So given a particular code word pair, C1KN, C2LN, so you output, so the estimate xn hat yn hat, it outputs the following. So it's equal to some particular pair xn tilde yn tilde. So it outputs a particular pair if, so it looks at all possible sequences. So among all possible sequences which are mapped to this pair of code words, it identifies that pair, that unique pair, which are jointly typical. So if xn tilde yn tilde is in the jointly typical set pxy, and so of course the ENC of x1 tilde should be equal to C1kn. So of course x1 tilde has to be, sorry, xn tilde has to be encoded to C1kn. Yn should be encoded to, yn tilde should be encoded to C2. The pair should be jointly typical, and no other pair xn yn with the encoded form of xn and yn being equal to C1 kn C2 ln is in the jointly typical set. Okay, so basically what is happening is the following. Okay, so this is, so if this does not happen, if either one of these are violated, so let us say that there is, so xn tilde yn tilde is not in the jointly typical set, or there is more than one pair, if there is more than one pair which are jointly typical and are encoded to C1 kn C2 ln, then you just map it to, say, one particular sequence. Okay, so it is equal to, let's say, 0 sequence. If more than one pair of xn yn which are encoded to C1 kn C2 ln are in the jointly typical set. All right. Okay. So let's see what is happening over here. So we can draw this particular table, right? So with xn's and yn's. So this is y1n, y2n, and so on. And this is x1n, x2n, and so on. So this is all possible xn's and all possible yn's. So corresponding to each xn, yn pair, we have a particular pair of code words. Okay, so let us say that the pair of code words is say 0, 0, maybe 1, 3, so on, whatever, right? So you have some particular, so basically what you do is for each pair, you identify a pair of code words. All right, so let me draw this instead of writing down the binary sequences which correspond to each particular xn, yn pair, let me instead draw them in terms of colors. Okay, so the red color corresponds to one particular pair of code words. So maybe red, blue is one pair of code words. There could be other sequences which are mapped to red, comma blue. There could be some which are mapped to blue, blue. There are some which are red, red, and so on. So similarly, all of this could happen, right? So for each pair of sequences, you identify a pair of code words. For each pair of code words, there are multiple x and y n pairs which get mapped to the same pair, right? So for example, for the red code word pair, there are these sequences. There's one sequence, there is this sequence, this pair of sequences, there is this pair of sequences, and there is this pair of sequences which get mapped to the same pair of code words, right? So it is possible that corresponding to one code word pair, there are multiple jointly typical x1, yn pairs, and it's possible that for some code word pairs, there's a unique jointly typical pair, and for some code word pair, there could be no jointly typical pair, right? So think of it as though you're throwing balls in bins, all right? So the balls correspond to pairs of code words. The bins correspond to code word pairs. Xn, yn pairs, and the bins are code word pairs.
Sir?
Yes.
Sir, can you once more explain how decoder is decoding the code pairs?
Okay. So the decoder will first see a pair of code words, right? So this is the model, right? So xn is compressed to some c1, yn is compressed to some c2. The decoder sees this particular pair, c1, c2. So it's some pair of binary sequences. So now there could be multiple, so this table, right? So these tables are accessible by the decoder. The decoder knows these tables. So it looks at these tables and identifies which xn, yn pairs correspond to this particular code word pair. Okay, so maybe the code word pair was 0010, comma 01101. Okay, so given this, so the decoder sees these pair of sequences and finds out which all xn, yn are actually mapped to this pair of code words. Right? It looks at these tables and finds out which all pairs are mapped to this. So those are the candidate. So let's call them candidate pairs. Okay. Among all possible candidate pairs, if there is exactly one pair which is jointly typical, then the decoder outputs that. Okay. So for this particular 0, 1 0 0 1 1 0 1. So this is the code word pair. Now there could be multiple pairs of xn yn. Let's say x1n y1n, x1n y2n, maybe x10n y20n, and x100n y2n. Okay, maybe these pairs all map to this pair of code words. So x1n is mapped to this, x10n is mapped to this, and x100n is mapped to this. Okay, and so there are, and y1n is mapped to this, y2n is mapped to this, y20n is mapped to this, and y2n is mapped to this, and there could be like multiple such sequences which are mapped. So now you have a list of candidate message pairs for this particular code word pair, right? So among these, some of these could be jointly typical, some of them may not be jointly typical. So in this list, if there is exactly one pair which is jointly typical, then the decoder outputs that. If there is exactly one jointly typical pair. If either there is more than one pair or no pair, if none of these are jointly typical, or if more than one are jointly typical, then it just outputs some random pair of messages. Let's say zero messages. Okay, so that is what the decoder does. Is that clear?
Yes, sir. Sir, one more question.
Yes.
How do we check that joint typicality of?
So that's, again, you have another table which consists of all possible jointly typical sequences, and then you check against that table.
Yes.
Okay. So again, this encoder and decoder, they're not computationally efficient. Okay, that this can do this, but they're not going to be good. Right? It's possible to implement them, but implementing them is going to take a very long time. Okay, at the end, after we see the proof, I'll indicate as to how one can reduce the computational complexity. There are other tricks one can play. Okay, in particular, you can employ linear encoders and decoders in order to reduce the computational complexity, but we'll get to that later. So right now, I'm just implementing everything in terms of tables. I have both the encoder and the decoder have these code word tables, and the decoder also has the table of all possible pairs of jointly typical sequences, and it just checks against them.
Sir, which means basically every code word have some kind of PMF with respect to the.
Yes. So right now we're assuming that xn and yn are random sequences, right? So
yes.
we're going to have this. Yeah. So the assumption is that xn and yn are drawn IID according to pxy. This pxy, the joint distribution, is known to everyone. It's known to both the encoders, it is known to the decoder. And you're going to use this pxy to design the code book and to design the decoder. So this is known beforehand.
Okay, sir.
Okay, and one way to know it is to estimate it. So you just observe some pairs of sequences. For example, if you have say if these are two sensors deployed somewhere, then you first take a few samples, estimate what the joint distribution is, and then use this to design the encoder and the decoder. Right?
Yes, sir.
Okay. So this is how the decoder works, right? And so if any one of these things are violated, then it constitutes an error. And now we want to show that if you choose the parameters well enough, then the average probability of error is actually vanishingly small. Okay, so let's analyze the probability of error. All right. So what are all the sources of error? So the first source of error is that the actual messages So let's call this E1. Okay, so the actual messages are not jointly typical, not in E epsilon n of Pxy. Okay, so that is one source of error. So if they are not in the jointly typical set, then the decoder will obviously not output that particular pair xn yn. Right. The second source of error is that well, xn is typical. So xn is in the epsilon n. So both xn yn are typical. Could be in the typical set or not, but there is some other pair which is jointly typical. So not just xn yn, but some other pair could also be jointly typical. And now there are three possible cases. So it's possible that some other, so xn and yn prime or yn bar are in the typical set. Epsilon n for some yn bar which is not equal to yn. All right, so this is the first case. The second case is some xn bar and the true yn are in the typical set. And the third case is that some other xn bar yn bar are in the jointly typical set. Right. So the decoder succeeds only if xn yn is in the jointly typical set and no other pair is in the jointly typical set. So if there's any other pair, then that constitutes an error. And for that we look at three different cases. One where the true xn and some other yn bar are jointly typical. The second case is when some other xn bar and the true yn are jointly typical, and some xn bar, yn bar which are different from xn and yn are jointly typical. Okay, and we'll analyze each of these error events separately. All right. So the first error event, this is easy to analyze. We've seen that the probability that E1, so the probability that xn, yn, which are drawn IID, are not in the jointly typical set. Pxy, this anyway tends to 0, right? So we know that this is bounded from above by some e to the minus alpha times epsilon square n for some constant alpha. Right? This is basically property of jointly typical sets, which we've seen in our previous classes. Okay, so this is what we've already seen. Now let's analyze the other event. So this probability is vanishingly small. Now let's show that each of these three events are also vanishingly small. Okay, if we show that all of these are small, then just by the union bound, the overall probability of error, which is the probability that either E1 or E2 occurs, that is also vanishingly small. Just use the union bound, so it's less than or equal to the sum of the probabilities of errors. and therefore the sum of the probabilities of the error events, and therefore if each of them are vanishing in n, then the sum is also vanishing in n. All right. So let's look at the first probability, which is that xn and yn tilde are in the jointly typical set. So this has to happen. T epsilon n of pxy, and so note that this has to be in the jointly typical set, and these two are encoded to the same pair of code words, right? So and encoder 2 encodes yn tilde to the same code word as the true message yn. Right? So this is what, so we want to find out what is the probability of this happening. Right? So this is basically the sum over all possible yn. So let me call it, I guess I should call it yn bar, right? Yn bar. So you will take the sum over all possible yn bar of the probability that yn bar xn yn bar are jointly typical epsilon n of pxy, and the encoder encodes yn bar to the same code word as yn, the true yn. Correct? Okay, so this is what is actually happening. So this I claim. So what is the probability that a particular right? So what is the probability that some particular yn is mapped to the same code word as what is the probability that yn bar, a given yn bar, is mapped to the same code word as yn, right? So that's what we're interested in. And we're summing over all possible yn bar which are jointly typical with respect to xn, right? So I will split this in the following way. I'll sum over all possible xn, okay, probability xn equal to xn, summation over all yn bar, probability that xn yn bar are jointly typical y, and the yn bar is equal to yn, right? But what is this? So this is the same as saying equal to xn summation. So we're interested in all yn bars which are jointly typical with respect to one particular xn. So basically we are only interested in those yn bars which are in the conditional typical set. Pxy given xn, right? So this is the probability that the encoder encodes yn bar to the same as yn. Correct? So, but what is this probability equal to? So you fix any particular sequence. So, so note that this is a sequence of length ln, and the code words for each yn bar are drawn uniformly at random. So what is the probability that this is equal to some particular ln length sequence? Yes, so what is this probability equal to? So suppose that the true sequence yn is mapped to the all zeros code word. Okay, so it's 0 0 0 0 of length ln. Right. So and now for yn bar the code word is drawn uniformly at random. Right. So what is the probability that this is equal to the all zeros code word? Yes, anyone? So ENC2 of yn bar is uniformly distributed in 0 1 to the ln. All right, and ENC of yn or ENC2 of yn is it's some particular sequence, let us say. So what is the probability of that the code word for yn bar is equal to the code word for yn? So what is this probability?
One by 2 raised to power k log n.
Yes, so it's whatever 1 over 2 raised to ln,
Yes, sir.
right, or 2 to the minus ln. Okay, so that is 2 raised to ln. Right, so it's 2 to the minus ln. So this is simply summation over all possible xn, the xn of xn times 2 to the minus ln times the size of the conditional typical set, right? T epsilon n of Pxy given xn. Right, but what do we have an upper bound on the size of the conditional typical set? We've seen this before, right? So it is 2 to the n times
hx plus
h.
hx minus epsilon.
No, so it's just h
Oh, sorry,
y given
h
x,
of
right?
equal, h of y given x.
Yeah, so it's h of y given x minus some function of epsilon, right? So sorry, plus some delta of epsilon, right? So this is basically, so since we're just summing, so we can take these two terms outside and sum over all possible xn. So this is equal to 2 to the n times h of y given x plus delta of epsilon minus ln. So as long as ln is strictly greater than whatever, if as long as ln over n is strictly greater than h of y given x plus delta of epsilon, this probability tends to 0 as n tends to infinity, right? So, and that is indeed, we are choosing R1 and R2. So you know that this converges to R1, which is greater than h of y given x plus some epsilon. And therefore this probability tends to 0 as n tends to infinity. All right. So similarly, even in the second case, you'll get that the probability of the second event happening is upper bounded in a very similar fashion by 2 to the n times h of x given y plus some delta of epsilon minus kn, right? And as long as kn by n is greater than h of x given y plus delta of epsilon, this probability is vanishing in it. And an identical calculation gives you that the probability of the third event is less than or equal to 2 to the n times h of x comma y plus some delta double prime of epsilon minus kn minus ln, and this tends to 0 as long as kn plus ln by n is greater than h of x comma y plus delta double prime of epsilon. Right? So each of these probabilities tends to 0 as n tends to infinity, and therefore the overall probability of error is also vanishing in it. Right? Okay, so let's stop at this point. If there are any questions, then I can answer them. It's basically what we did was we analyzed different error events, and we show that each of these the probability of each of these error events is vanishing in n, as long as the rate is sufficiently large. Right? As long as you choose rates which satisfy these properties, the probability of error is vanishing in it. All right, so any questions? Okay, so we'll continue. In that case, we'll continue in the next class.